So, to find the gradient of a straight line, doesn't matter what type of straight line we have, it's just a straight line. We choose two arbitrary points, x1, y1, and x2, y2. And what we do is we take the difference in y values and the difference in x values. So what we do is we go down and we go across. We do y2 minus y1 here and x2 minus x1 here. And the gradient, which is defined as delta y over delta x, is equal to y2 minus y1 over x2 minus x1. This is the expression to find the gradient of a straight line. So we clearly need 2 points, 2 sets of coordinates in order to find the gradient. And also, to clear up some terminology, y is known as the dependent variable, and x is the independent variable. So we've just taken a look at how to find the gradient of a straight line. And now we're going to try and extend this to not just a straight line, but any little curve we've got here. So we're going to take a curve in the closed interval from x equals a to x equals b. And we're just going to assume that the function is well behaved and continuous, just so it makes this easier for us. So we're going to choose an arbitrary point in this interval, and let's go right here, and let's call it x0 f of x0. And close bracket. Now, our question is to find the gradient of this curve, y equals f of x, at this exact point. Now, going back to lab, or science lab, I should say, when you were given data and you had to draw a curve of a sphere, and then you were asked to find, the initial rate of change. Since you don't know an analytical expression for the data to model the data in, you essentially had to do the classic method of drawing a good enough tangent and finding its gradient and saying, hey, this works, let's just do it. So the issue with that is we don't have that sort of luxury. We're not working with some predefined scale where this is 1, this is 2. Like no. We don't work with that, unfortunately. But the question is, how do you find the gradient? And the next question is, can we do this for any point? The answer to that question is yes. We want to find the gradient of this tangent, and this seems simple enough. We just choose a point here, and we're just like, cool, change in y, change in x, done. No, because like I said earlier, we do not have any scale. We do not know what this tangent is. We do not know any point on this tangent as a result, except this point x0 f of x0. We have nothing else. And also remember that change in y over change in x is equal to y2 minus y1 over x2 minus x1. i.e. we needed 2 points to calculate the gradient of a straight line. But here we only have 1 point because we don't know any other point along this so-called tangent. And that poses a problem for us, because now we need to figure out a way to get this tangent somehow. So what can we do? Well, as any physicist's best guess, we approximate. We're going to choose some other point along this curve that's somewhat close to it, but let's just be a bit frugal here, and let's just choose some point up here. I'm going to call this x1 f of x1. And so what we do is we draw a chord. And a chord is simply just a line segment, right? It's the same type of chord that we get in a circle, it's just a line segment. But that's besides the point. We draw a chord, and what we do is we find the gradient of this chord. We have f of x1 minus f of x0, and we have x1 minus x0. So this means we get our gradient, change in y over change in x, to be f of x1 minus f of x0 over x1 minus x0. That's perfectly fine. Alright, sure. But as you can see, this red line is nowhere near looking like what this yellow line is looking at. This chord does not look like this yellow tangent. So what can we do? We can attempt to improve our estimate. So let's do it again. Let's now go even closer. And what I'm going to do is I'm just going to zoom in, right? I'm going to zoom in a bit. So we're going to zoom in here. We're going to do that. And what this gives us is essentially something that looks like this. We have a bit of the blue. We have our original point, x0, f of x0. And what we're going to do is now, instead of going relatively far away, we're going to go quite close to it. We're going to go to some random point, and we're going to call this x0 plus h and f of x0 plus h. And I'm going to draw chords connecting the 2 points. It can look something like that, maybe. I'm also going to draw a tangent, just so you can see what's happening. Actually, we're going to draw a tangent that looks a bit like this. Okay, so you can see that it is a terrible drawing, I know, but our chord is slowly and surely approaching what this tangent looks like as we approach the point, i.e. this constant h is getting smaller. It's going to be approaching 0. That's the key idea here, because when it is 0, we arrive at our point. So let's find the gradient of this chord, right? So we have delta y over delta x. It's really just f of x0 plus h, right? It's the change in the output, the change in the dependent variable, over the change in the independent variable, the change in x. Luckily, those nicely cancel out. So we're really just left with this expression, x0 plus h minus f of x0 over h. Now, if we do let h equal 0, then it means our gradient, delta y over delta x, becomes f of x0 minus f of x0 over 0. This is already bad. This dividing by 0 is bad. However, if we even cancel the numerators out now, because clearly they're the same thing, we have 0 over 0. And this is really bad. An even sadder face. So what we need to do is we need to consider what happens as h goes to 0. Instead of considering what happens at h equals 0, we consider what happens as h equals 0, as we're approaching h equals 0. And this is where we introduce the notion of a limit. Now, this isn't a series about limits, this is a series about derivatives. We are dissecting derivatives. And so I'm not going to formally introduce what the limit is here. But for now, informally, we can think of it as taking an expression and making it approach something, right? So if we have the limit as h approaches 0, because remember, we want this to go to 0, we want this point to eventually become that point, of f of x plus h minus f of x over h. Now, first thing I want to note is I have changed x0 to x. This is because, remember that we can find the gradient of the tangent at any point along any curve or any curve defined in a certain interval along a certain domain. We can do that. So we can just replace some certain x0 and just replace it with x, any x that is, of course, defined properly. And so it's this idea of taking a limit, so eventually the difference between these 2 points becomes 0, that we want to use. And it's this expression that is the absolute crux when it comes to differentiating. There's different ways we can denote the derivative. One of these, I don't really know the names, but apparently it's called Leibniz notation or something. Well, that's not the point. The point is we write something like this. We have dy over dx, and we have df by dx. Now, where does this d come from? Well, informally, because remember that delta y over delta x really is more like an average gradient, right? Because remember when we found the gradients of the different chords, that wasn't the exact thing. But now we're making these infinitesimally small. And so we denote this by dy dx rather than delta y delta x, because this essentially now becomes exact. It becomes instantaneous. It's the instantaneous exact gradient at a certain point. And that's how we get dy dx or df by dx. Now, again, notation-wise, the dependent variable is on the top, and the independent variable is on the bottom. And that's again how notation works. What we've been using throughout is function notation, where we have f of x and f prime of x. We can also just put primes next to various letters. The only issue with that is you don't necessarily know what letter you're differentiating with respect to, because remember here we're specifically saying we differentiate with respect to x. X is our independent variable, whereas here we don't necessarily know, but from context we probably do know. Now, next thing is dot notation. And dot notation is really used for a specific derivative. It's specifically used when differentiating with respect to time, generally denoted t. And in physics and kinematics, this is what's generally used, so it's easier to write. And this is generally also read out loud as the rate of change of x. And finally, these little things, multivariable calculus notation, if you will. This is a nabla symbol. It's an upside down delta, if you will. And this is a partial symbol, which is like a weird, which some people call a weird D or weird delta. And this is when we have a function of multiple independent variables. When we have something like f of x, y. And we might only want to differentiate with respect to x and not y. So we use a partial derivative. This we won't touch pretty much at all until we get to multivariable, calculus. So don't worry about this for now, but this is some notation that's used for the derivative. In general, we're going to focus on these two and this when during physics. So anyways, I think in terms of a summary, this is all you need to know. Just this expression, that's it. Thank you for watching. See you in the next one.